yeah, so this is the last talk of this week, and we are very happy to have Greg Valiant from Stanford to talk about the estimation beyond the IID setting. So take away, Greg.
Okay, so thank you, and sorry I'm not there in person. Good. So I was going to talk about, I guess, two different sorts of challenges that happen when you're trying to do learning or estimation beyond the kind of IID data setting. They're quite different, and it's okay if we don't get to both parts. Oops. Okay, so the first part is based on some joint work with Justin Chen, who's a PhD student at MIT, and Paul Valiant, and it appeared at this past Theorems. So as a warm-up, I wanted to start with sort of the most simple possible setting, and a sort of surprising result that I wasn't aware of. So suppose we're just trying to estimate the bias of a coin in a worst case optimal way, and I'll explain what that means in a minute. Okay, so I have a coin. There's the coin has some secret bias, and your job is to guess the bias. Okay, so here's my coin. And suppose I'm just going to flip the coin once. Okay, so I flip it once. And your job is to guess the bias of the coin in a way that's going to minimize the expected error, the expected squared error of your guess, in a worst case sense. So in the worst case, overall possible bias is P. So suppose I know your algorithm, I know how you're going to map an outcome to a guess, and I pick the P that maximizes this expected error, and then I flip that coin. What algorithm do you use that minimizes this? Okay, so let's try something. So suppose I'm going to flip the coin. Okay, so I flipped it, and we get a 0. And now, based on this data point, your job is to guess the bias of the coin in this sort of worst case optimal way. So so what's your guess going to be? So someone in the audience should guess something. It's okay if it's not. I'm sorry, say that once more.
Half.
Sorry, a half?
Yes, a half.
Oh, a half. Okay, so okay, that's not a bad guess. And here, let's do one more guess. One more guess.
0, yeah.
0. Okay. Okay. So the right answer is actually halfway between those two guesses. So I claim that the sort of worst case optimal, and again we'll parse what we mean exactly by this. Sort of mapping is if the outcome's a 0, guess that the bias is a quarter, and if the outcome's a 1, so by symmetry you'll guess that the bias is 3/4. So I guess, to show that this is sort of optimal requires a tiny bit of calculation, but just as an intuition, suppose if the outcome is 0, you guess that the bias is 0. If the outcome is 1, you guess that the bias is 1. Well, in that case, if the bias is close to 0 or close to 1, you'll do very well in expectation. But if the bias was a half, then your squared error will be, well, a half squared, it will be a quarter. And so in that case, the kind of worst possible P would correspond to being exactly a half. And the best P would be kind of P equals 0 or P equals 1 from the perspective of your algorithm. And this sort of proposed algorithm where if you see 0, you predict a quarter. If you see 1, you predict 3/4. This sort of trades off the error at P equals a half versus the error at P equals 0 or 1. And it sort of balances it out. And by some sort of, convexity type argument, intuitively, it seems like this is going to be the best thing. And, if you actually compute this, for all values of P that are between something like that are between 0.07 and 0.93, this is going to get better expected error than if you say just outputted 0 if you see 0 and 1 if you see 1. Okay, let's do this for 2 flips. So suppose I flip the coin 2 times, and again, sort of by symmetry, if you see a 0 and a 1, or a 1 and a 0, you should predict a half, right? So by symmetry, if half the things you see are 1, half are 0, you should be estimating a half. So the only question is kind of, what should you predict if you see 2 zeros or if you see 2 1s? And again, by symmetry, the answer for the zeros should be 1 minus the answer for if you see 2 1s. So really the only question is, if you flip 2 zeros, what are you going to estimate? What's your estimate going to be? Does anyone want to throw out a guess?
1/6.
Okay, not bad. So it ends up being, so we'll see exactly what this expression is. It's going to, this expression will have some square root, some square roots in it. But yeah, it's not too far from a sixth, but yeah, it's 0.2 roughly. Good. Okay, and okay, so I'm spilling the beans. So if you flip k times, the optimal, from this kind of worst case perspective, estimator, it takes the empirical estimate, the mean of the samples, and it's going to regularize it. It's going to smush it a little bit towards a half, and it regularizes it towards a half with this weight that's kind of 1 over the square root of the number of flips plus 1. Okay, so it's and this turns out this was has been known for actually over 70 years. So there was a paper on this problem by Hodge and Lehman. I feel like I'm misspelling one of these names, but that's okay. In Annals of Statistics in 1950. And in the paper, they sort of say that someone else knew this earlier. I think Rubin maybe knew it even earlier, but maybe it wasn't published. Good. So one thing that's surprising about this, just to sort of so what's not surprising is that you're going to kind of, when k is small, you'll mush things a bit towards a half. What I found surprising, and what sort of this paper ends up claiming should be surprising in some sense, is that this estimate is linear, in that it's a linear function of the sample mean. And there's no reason that there's no reason that you would necessarily guess that the right answer would be this linear function of the sample. Okay, good. Before I go on, is there any questions about either what this specific problem is, or what these numbers mean, or how to think about this? Okay. And just out of curiosity, is anyone in the audience, had anyone in the audience actually known about this formula?
One person's putting up their hand. I don't know if you can see it, but my question is, can you define exactly, sorry, what you mean by blah, blah, blah for the worst case P? So, good.
So, okay, so given an estimator, so your estimator takes the outcomes and maps it to some prediction. For some fixed true bias P, like suppose my bias is, a third.
Yeah.
So for a fixed bias, you can say, what's the expected squared error of your estimate, right? And that's kind of the natural metric, say, for measuring. And here we're going to be, we're concerned with this expected squared error of your estimate, but where you take the maximum over all the possible biases P. Sorry, I can't hear, but does that make sense?
Yeah, it made sense. Thanks. So yeah.
Okay. And again, like, if you have a bound on this worst case, expected squared error, then you can make the claim that whatever the true bias is, I have an estimator where the the expected error is blah, right? So no matter what the true bias is, this is how I'll improve it, which is a nice bound to have, right? You don't need to. Okay, and of course, in this case, maybe it's not super exciting because as k gets large, just the average of your samples is going to converge well, and that's fine. But okay, good. Any other questions? Oh.
This is great, and I'm very happy to learn it. But it also seems to show that where biased coin flips are concerned, the squared error is a wacky loss function.
Oh, okay, good. So why do you say that?
Well, because there are other loss functions, like, for instance, the log likelihood, which would give the more natural estimator. And it's not as if our noise is Gaussian, and why in the world would we care about the squared error in this case anyway? Besides the fact that we care about it in lots of other places where distributions are Gaussian. But this is a snarky question. This is awesome. Thank you for showing it to us.
Yeah. Okay. So good. So and yeah, that point's certainly valid. Although for other settings and for other losses, one can get similarly strange answers too. But yeah, no, that's certainly valid. Good. Okay, so let me give an alternate formulation of this problem, which will be the jumping off point for what we're really going to talk about. Okay, so again, this problem was, we're flipping a coin k times, and we're trying to estimate the bias of the coin in an optimal sort of perspective from the expected squared error from a worst case perspective. Let me phrase this in an alternate way. So suppose we're given n different binary outcomes, or sorry, suppose there are n different binary outcomes out there, x1 through xn. And there's no coins behind these x's. These are just some values that are sitting out there in the universe. And now suppose we're going to be given a uniformly random set of k of these outcomes. So for example, suppose we're told, well, x sub 15 equals 1, x sub 19 is 1, blah, 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 x sub 100 is 0, and so on. So given this random subset of k of these values, our goal is going to be to estimate the overall mean of all of these values, again, so as to minimize the worst case expected error. And let me write that out. So we're trying to find an estimator, some function f, that maps these k kind of observations to some prediction. And we're going to try to find the estimator which minimizes the worst case, the maximum over possible values that these x's have, of the expected error, where again, the expectation will be over the choice of which of these k things we see. So the expectation is over a uniformly random set of k of these things. And what we care about, again, is, say, the squared error, the difference between our prediction and the true mean of these things squared. Okay, so I claim that as n goes to infinity, as the kind of number of these underlying values goes to infinity, this problem is exactly the same as we're given k independent flips of a coin, where the kind of bias of the coin corresponds to the true average value of these x's. And this is the same problem as what we just talked about. Does that make sense? So, good. So, in the case, in the case where what we observe is a subset of, a uniformly random subset of k of these observations, there's this nice, beautiful closed form solution to this optimization problem. And the question that we're going to think about is, well, what if the observations are not drawn in a uniformly, are not a uniformly random subset of K? What if the observations are drawn according to some other sort of distribution? How can we still try to solve this problem? Okay. So suppose, okay, so we're going to step back a little bit and come back to this. But basically, we're thinking about the setting where we have these, you can think of their, well, okay, we'll come back to this. Okay, so stepping back a little bit, it would be really great if we could be able to accurately estimate some statistics of some underlying populations. In the case where the data that we see, the sort of sample that we observe is sampled according to some sort of complex data collection process. So maybe samples are still independent, but it's not it's not identical. So maybe there's some important sampling, some elements of the population have a higher probability of participating in our sample than others. Or maybe things are much worse. Maybe the samples are very dependent, whether a given element of the population is in the sample is correlated with whether other things are. And there are obviously lots of kind of real world sampling processes where there are, there's a lot more sort of structure and correlations. So one example is this kind of snowball sample, or also known as kind of respondent-driven sampling, which sort of arises a lot in social science surveys and some medical type stuff, where you basically, well, you can think of it as there's some, say, social network over the population, and when one person responds to a survey, there's some probability that each of their friends also responds. Okay, so this is like the sort of thing where if you respond to a survey, I'm going to say, hey, by the way, I'm going to give you $5 for every friend of yours that also, everyone you refer to who fills out the survey, I'm going to give you $5, and I'll give them $5, and so on. Good. Okay, and again, so the sort of usual way that maybe people think about estimation and learning is where we have these distributional assumptions about the data values. So each of the xi's is picked from, is a coin flip or distributed like a Gaussian or something like that. And sure, there are lots of generalizations and sort of extensions of this. So, having robust statistics, there's still this distributional assumptions about some of the data, right? So robust statistics, you assume that maybe a portion of your x's are drawn from some nice distribution, and maybe you make no assumptions about the remaining ones. But instead, we're going to think about the kind of setting on the right, where we're not going to make assumptions about the data values, about the xi's themselves, the values. Instead, we're going to try to leverage an understanding of the sampling process, the decision about which xi's are in our sample. Okay. And we'll see exactly what we mean by this. Okay, good. So let me just re-describe the framework, which was basically the same framework we started at the beginning. So suppose there are n entities. So sorry, I drew these as people instead of as coins. Each person, say, has a hidden value. So the ith person has some value xi. Let's think of this as a bounded real number. We can think of it as being some vector later on, but for simplicity, let's think of it as just being a single real number, say bounded between, I don't know, -1 and 1. Our goal is going to be just to estimate the mean of these n values. And again, we can think of other statistics, but let's deal with that later. Okay, maybe I'll keep, well, okay, we can have a running example on the right side of the screen. Okay, and then crucially, let's assume that we have there's some known distribution P, capital P, which is a distribution over subsets of these n people. And we think of this as being kind of the sampling distribution. So what happens? A subset of these n people is drawn according to this sampling distribution P. We observe, who's in this subset and the values, the x is indexed by the people in this subset. Okay, so in our running example, suppose the first 500 people are going to respond to our survey with probability 0.1. The next 500 people are going to respond with probability 0.5. And oops. Good. Okay, and we're going to make a prediction, which is going to be a function of this distribution, this known distribution over subsets P, as well as a function over, well, who ends up being sampled and the values that we see in that sample. And we're going to be trying to find a function f that minimizes the worst case expected error. So we're going to try to find a function that minimizes the worst case over the different values that the people might have of the expected error, where the expectation is over the randomness of the subset that we actually have in our hand. Okay, and in this kind of important sampling setting, there are plenty of estimators that do reasonable work, right? So the standard estimator that just weights each of these samples kind of 5 times more than these samples, we'll end up having a small worst case expected error. Yeah, sorry, there's a question. Yeah.
Hey, sorry, this is just a minor clarification. So, I mean, there's like this long line of work in statistics, which is about like finite samples or like finite populations and randomization inference. I'm just trying to understand, is this minimax estimation in that setting, or is there any difference to that?
Sure. So you can think about it in that setting. You could also think about there being a, say, countably infinite underlying population. That doesn't really matter. This notion of caring about the worst case expected error, it's not sort of the typical, it's not the typical framework, but it's certainly, I mean, this paper from 1950 in Annals of Statistics was also within that framework. So, I mean, I guess the new thing that we are trying to do is make kind of one algorithm which takes this distribution P and does the right thing, for every distribution P, will compute the optimal function f.
I see. Okay, thanks. Thanks so much.
Right. So yeah, so the framework is not,
Actually, I also have a question, Greg.
Yeah.
So in your example, I think P is a product distribution. If we treat that as a distribution, let's say over the vertices of a binary hypercube. So yeah, is there any example in your mind where P is not a product distribution?
Yeah, good. So I think I'll do that I'll have some examples on the next slide, I think.
Okay, great.
Or maybe 2 slides from now. But if I don't answer that within 5 minutes, I'll come back. Okay, good. So actually, maybe there are 2 tasks. So one task is, suppose someone gives you an estimator f. They describe this function. Can you even compute the worst case, or compute or approximate the worst case expected error? Can you tell me, like, what's the worst data distribution? Sorry, what's the worst kind of data values for your estimator? And then, of course, there's the even harder task, which is, can you find the best estimator, the function f that minimizes this kind of worst case expected error? Okay, so there are these two tasks that we might care about. Good. Okay, and again, I guess just to go back to this running importance sampling example, suppose you give me some algorithm, say the standard algorithm. The worst case data for this algorithm corresponds to saying, what's the kind of worst case way in which the data values, the x's, might be intertwined with these probabilities of participating in the survey. Okay. And this is, very, like, from a kind of practical standpoint, this makes a lot of sense, right? Like, if somebody is going to participate in your survey with probably 0.1, and someone else might participate with probably 0.5, presumably their data values might also, kind of be drawn from very different, be quite different, reflecting the fact that these are people who behave differently. And this worst case framework basically is going to say, look, we want our algorithm to work even when the values might be arbitrarily, sort of adversarially colluding with these underlying probability distributions. Okay, good. I wanted to just mention that everything we're going to talk about also goes through in this slightly more general setting, where instead of trying to estimate the mean of the population, the mean of x1 through xn, suppose there's also some target set that's drawn according to some other distribution, and we only care about the mean of this target set. Okay, so you can think about it as the goal of estimating the mean of the overall population, or that there's kind of some, you can think about the sample as being a training set, and there being some other set T, which is the test set, and we were trying to estimate our statistic on the test set given the data in the training set. So anyway, so the whole framework goes through in this setting too, and our results also go through in this setting too. Okay. Okay, good. So let me give some illustrative examples. So, okay, so we've already talked about these first two. So certainly this kind of importance sampling and just this independent coin flip setting, the underlying distribution over samples corresponds to this this kind of product distribution where each individual appears in the sample independently, with maybe some individual specific probability. Something like this snowball sampling procedure. In this case, the this distribution capital P is very far from a product distribution, just because if your friends are in the sample, it greatly increases the chance that you'll be in the sample. A different setting, which I wasn't planning to talk about too much, is the this kind of forecasting type setting, where the x1 through xn you should think of as being sort of a chronological sequence, and we're going to end up observing some past data x1 through x sub t, and we're going to be asked to predict something over some future set, like x sub t plus 1 through some other x sub t plus w. And again, in that case, there are obviously strong dependencies between which data points are in the sample, and so on. Is that okay? Okay, so let me describe the main results, and I'll sort of sketch out how the arguments go very briefly. So the first theorem says, if you're given some estimator, f, then in polynomial time, with a polynomial number of samples from this distribution over samples p. So we don't need to know the actual distribution p, you just need some polynomial number of samples. One can get a pi over 2 approximation to the worst case expected error of this estimator. Okay. And there's this caveat at the end that I'll mention in a second. And the second theorem is basically saying that actually in polynomial time, not only can you estimate the worst case expected error, but you can find an estimator that optimizes this, again, up to that same pi over 2 factor. And the caveat is that we're restricting ourselves in both cases to the set of estimators, which I guess we're going to refer to as semi-linear. And what does that mean? That means that your estimator is going to be some weighted combination of the values you see, but where the weight you put on each value can be some arbitrary function of this distribution P, as well as the specific set of people who are in your sample. Okay, so you can think of it as the set of estimators before you see the values. If you just know the list of people who are going to be in your sample, this defines a set of coefficients, and then they reveal their values, and you output this kind of linear combination of their values. So I should say, I can't think of any even vaguely reasonable non-semi-linear estimators, but still, this is a significant restriction. Okay, good. So let me begin by illustrating a little bit about kind of what this problem is, and sort of at least alluding to the kind of combinatorial structure of this problem. Okay, so suppose we were just looking at this problem of someone gives you some function f, an estimator f, and we're trying to figure out what's the worst case data for this algorithm. Okay, what's the worst case underlying x's that maximize the expected error of your estimator? Okay, so let me give you actually a very special case of this problem. So suppose this distribution P corresponds to the following. Suppose there's just some underlying graph over the n individuals, and this distribution P is defined implicitly as follows. We're going to pick an edge of the graph uniformly at random, and one of the endpoints, and I reveal the data value at one of the endpoints of the edge and ask you to predict the data value at the other endpoint. So I pick a random edge, I tell you the value at one endpoint, your job is to guess the value at the other endpoint. Okay. Okay, so suppose this is our distribution P, and suppose I'm going to tell you a trivial, it might not be a good algorithm, but I'll tell you a simple estimation algorithm, namely just whatever value you're told, predict that the other endpoint is equal. So suppose that's your estimation algorithm. Someone tells you the endpoint of the edge, and you predict that the other endpoint is the same. What's the worst case expected error of this estimate? Namely, suppose this is your estimator, and now it's your job to put, say, bounded values. Say the values are bounded between -1 and 1. Your job is to put the values -1 and 1 at the endpoints of the graph, so as to maximize the error of this estimator in expectation over the randomness of P, namely over picking a random edge. You're trying to make these endpoints as different as possible.
Is the graph by far type?
Say for an arbitrary graph. Yeah. So what? Yeah. What is this problem?
Some eigenvalue problem.
Or it's a max cut problem.
Yeah, exactly. Right. So this is exactly the max cut. Right. So if the values need to be bounded between -1 and 1, you'll put values -1 and 1 at endpoints so as to maximize the number of edges that are cut. Because then, according to this distribution P, anytime you pick an edge that's cut, the estimator will be kind of maximally wrong. And if you pick an edge that's not cut, then your estimator will be completely correct, which is why you're trying to maximize the size of the cut. Okay, good. So good. So this shows a few things. One is that.
Sorry, I have a question. Yeah.
Please.
So how did you get it exactly to max cut? Because it's not that obvious that everything should be -1 and 1, right? Because you're comparing it to the mean. So if the max cut gave equal sizes, then I believe you, like on each side. But maybe that would like drag the mean too much or something. Yeah.
Oh, okay. I'm sorry. So sorry. So this was in this sort of extension of the framework where the goal is to estimate the mean of the values indexed by the set T, as opposed to the mean of the overall.
But I think the question is, why does it never make sense to have fractional values in between this one and one for the adversary?
Yeah. So sorry. So in the case where okay, so sorry. So in the case where so as described, we were trying to just predict this other endpoint. We're not trying to predict the overall mean of the values. In that case, then this really corresponds exactly to this kind of max cut relaxation, where you're allowed to put some, you're allowed to put a value that's not. But in that case, if you're looking at these kind of fractional cuts, you do want to make everything binary. Is that okay? Yeah. Yeah, and so even in the case where you're trying to estimate the overall mean of everything, you can still embed this sort of thing and get it won't be exactly max cut. There'll be something a bit different, but you still get this NP hardness of exactly estimating this worst case optimal. Sorry, the worst case expected error. Okay, but good. So there's hope, because at least there's a constant factor approximation of max cut, and maybe maybe we should hope for some constant factor approximation in general for this for this estimation problem. And okay, and so this ends up panning out, and basically let me very quickly sketch what's going on. So I claim that given some estimator f, what if the estimator f looks like there's a if the estimator f has a semi-linear property, namely that as a function of the set we're given, in this case S and T, and the distribution P, if there's a set of coefficients such that we'll end up outputting this weighted average of the x's, then we can basically write a generalization of the Gormans-Williamson STP that will yield this kind of pi/2 approximation. So I guess what's the right way of thinking about this? Well, we're still trying to assign say values between -1 and 1 to these n different x1 through xn. And for every different sample S in the support of our distribution P, that's going to induce some sort of loss term. And we can end up just writing down what this ends up being, and this doesn't look so different from the kind of the natural max cut problem for which, say, the Gormans-Williamson STP applies. And then there are a couple of issues. So one is that maybe this is some exponential sized STP because we have an exponential number of sets in the support of P. But this isn't too much of an issue, because you can argue that, well, if you just sample some polynomial sized number of these subsets, both the solution and the value of the STP shouldn't change by too much. And then to go from being able to estimate the value of this to actually finding finding an optimal estimator, this is sort of a convex duality thing. So rather than thinking about minimizing over the functions f, maximizing over the data values x, and so on, you can switch the order of these things via convex duality and end up sort of analyzing things, and it ends up kind of directly reducing to this positive semi-definite growth and decay problem, which is kind of where the pi over 2 comes from, if you're familiar with that. Okay, so let's see. So I should wrap up pretty soon. Is that the case? I forgot exactly when we began, but 5 more minutes, 10 more minutes.
I think we have maybe 10 more minutes.
Yeah. Okay, good. Okay. Okay. So let me just say a few things. So even though we end up with some, so theoretically we end up with some fairly large SDP, one can actually implement this, and the resulting algorithm actually ends up working quite nicely in a number of so settings that we've experimented with. So let's see. Right. So for a couple of different settings, one is just a simple importance sampling setting, another is a snowball sampling setting, another is kind of predicting the future forecasting setting. The kind of SDP solution we end up with corresponds to an algorithm with, with a decent constant factor better performance than kind of the standard things. Let me maybe just talk about the importance sampling setting, because that's the one where I was most surprised that anything interesting happens. Okay, so again, so think of this importance sampling setting. Concretely, there are 50 people. The first 25 will respond to a survey or will be present in our sample independently with probability 0.1. The next 25 people are in the sample independently with probability 0.5. So there are sort of two standard importance sampling estimators. One of them is reweighting, namely, the first 25 people, they each respond 1/5 as often as the second. So let's just reweight their contributions to fix this. So that for each of the people in the first half, let's weight them 5 times more than the people in the second half. So that's this kind of reweighting algorithm. The other natural approach is to say, look, there are two different subpopulations. There's a population that responds with probability 0.1. There's a population that responds with probability 0.5. Let's estimate the mean of each of these separately. And then let's just return the average of the means of these two separate populations. So that's what I mean by this subgroup estimation algorithm. And from a worst case data standpoint, both these reweightings are, both the reweighting and the subgroup estimation are, maybe a factor of 2 worse than what the SDP algorithm gives us. And for these two algorithms, it's not too hard to see what the worst case data ends up looking like. So suppose everybody in one of these, everyone in the first set of people, say they all have values +1, and everyone in the second set has values, say, -1. So in that case, if you're doing this reweighting, where you weight the people in the first half, so 5 times more than the people in the second half, you're going to end up paying quite a lot in terms of the variance in how many people you end up with in the first half versus the second half. And that's why this reweighting is so bad. On the other hand, if you do this subgroup estimation, as long as you get at least one person from each of these groups, you get 0 error. And this tiny error here is due to just the small probability that you don't get anyone from one of these groups, and it'll probably be from this first group. However, if each of these populations has, plus and minus, sort of say equal-ish numbers of plus and minus ones, then the subgroup estimation ends up being problematic because you don't get very many samples from this first group. So there's a lot of variance in your estimate in this first group. Okay. And you know, kind of this SDP algorithm in both, you know, these kind of bad cases does pretty well, and it ends up being kind of a regularized version of well, sort of a regularized version of this subgroup estimation, but ends up being something that's interpretable, but fairly unorthodox. But it seems to work, you know, work much better. Okay, let me skip the snowball sampling stuff and good. Okay, in terms of use cases for this, so obviously this was sort of presented in the case where like we know this underlying distribution P. You know, in most real life cases, maybe we don't know the sampling distribution P. Although in sort of designing clinical trials or some polling type settings, maybe we do control the sampling procedure. And then there are these questions of, well, how do we, you know, how can we design a sampling procedure P subject to some conditions, which will actually guarantee that we have a good estimator? The vast majority of use cases, we probably don't actually know the underlying distribution P. However, in most of these cases, we, you know, could certainly dream up various plausible Ps, and it would be worth stress testing the estimators you plan to use in light of kind of the worst case performance with respect to plausible distributions P. And I think this third case is really the main sort of area of application of this sort of framework. Good. So there are tons of open questions related to this. Let me just say one thing. So in many cases, there's no pi over 2 gap. So if you run our SDP on, say, the problem we began with, where you're just trying to come up with this worst case optimal estimator for the bias of a coin, then you end up with exactly that right answer, which is that formula from the 1950 Annals of Statistics paper. And it would be nice to have a sort of characterization of which distributions P don't, you know, which ones don't lose this constant factor in the optimality. Another kind of interesting point is, you know, our theorems had this caveat that they only applied to semi-linear algorithms. Via some kind of computer search, we found some setting for which a non-semi-linear algorithm actually was better than any semi-linear algorithm. But the biggest gap we could find is this factor of 1.004. And I strongly believe that there's a constant factor, that this gap can never be more than some small constant factor. Okay, I think that's a natural place to end.
Thank you, Greg, for the great talk. So yeah, any questions?
Hi, Greg. Thanks for the great talk. So I wanted to ask a question about whether you have a sense for when we use these kinds of worst case procedures, how much it might be sacrificing on like a typical case scenario. And I asked the question because I sort of, if I remember correctly from my courses on statistical theory, when I first learned this Hodges-Lehmann kind of thing, that it's like sometimes used as an example to not take minimax results too literally or seriously, right? Because it ends up super optimizing that worst case error at the expense of increasing the risk for a lot of other parameters that might occur. So I was wondering, just in the sense for the SDP approaches that you designed, whether you have a sense of the extent of that trade-off.
Yeah. So I was going to say, so one nice thing about this framework is that you can find you can see the worst case distributions. The STP will give you these worst case things. Sorry, the worst case data values, and then you can decide for yourself, is it reasonable? So for the importance sampling setting, like the sort of worst case for this subgroup estimation really is this thing where just the population is uniform. Like everyone has values plus minus 1, equally mixed. And that certainly seems very reasonable. The worst case for this kind of reweighting setting, ends up being this completely uniform within each group, but the groups are maximally different. And you could argue that that's maybe not super realistic, but it's also not so different. I mean, if you have some subgroups that have different probabilities of participating in a poll, what's to say that the value you care about isn't also correlated with which of these groups you're in, right? So in this case, the worst case for kind of these two things ends up being very natural. And the kind of worst case thing for the STP is, I think actually it ends up being sort of, the STP is kind of trying to trade off performance on these two things. So maybe the worst case ends up being lots of, like everything in between these two extreme points. So in this case, at least, if you look at the STP and you ask what's the worst case distribution for that, you get there are lots of different data values, which are all worst case. And so this maybe tells you that things are okay. For a snowball sampling type thing, so say you have some spatial sort of snowball sampling, like your points, think of these as being people in some geographic space, and close by people, have some increased probability of, if someone near you participates, that increases your probability of participating. Then the worst case data for sort of almost anything natural, but including the STP thing, ends up being some spatially correlated values. So maybe, up in the upper right corner, everyone's values near -1, and lower left, everyone's value is kind of +1. And again, this seems pretty natural. Like if you don't sample these people in the lower left at all, then it's maybe they're very different than the people in the upper right, and but yeah, so at least for some of these examples, you can look at these worst case data values and think about how realistic is it. Although I did, one of these, the last open question is, maybe new and practical blends of this model with more traditional models. So yeah, this last point was trying to get at is there something that's maybe not as pessimistic as this worst case, but still allows for bad sorts of correlations between, who ends up being in your sample, or sorry, bad correlations between kind of your sampling distribution and the underlying values that you care about. And I don't have any great candidate hybrids yet, but I think it's worth thinking about. Sorry, that was a long answer, longer than people wanted.
Thanks for a great talk. So when I think about, for instance, political polling, or for that matter, snowball sampling, it seems like the problem is in both cases, we don't know P. And worse, and maybe there's nothing to be done about this, people's probability of responding is actually correlated with the value they have. And so that, in a sense, the adversary first gets to choose the values and then gets to choose, to some extent, the distribution of subsets. And maybe that second part, there's just nothing to be done because, I could just say, well, some fraction of the people who have this value just don't ever respond. And whatever. But for the first thing, I mean, I was excited about the fact that your randomized algorithm, sort of subsampling the STP, talked about samples from P. So if you're taking samples from P anyway, then why doesn't this apply to a setting where you don't know P, but where you're able to try this polling process many times and get a sense of the distribution of subsets?
Okay, so good. So that's perfect. So yeah, so you don't need to know P, but you need to be able to get samples from it. And again, these samples from these samples, you don't need the X's for them, right? You just need to know who's in the sample, right? You don't need the data values. You just need to know who's in the sample. So I think in terms of the political polling setting, I think the hard part, I mean, this does apply to that setting. I think the hard part, though, is that we don't have many samples from P, in the sense that P changes very rapidly, right? So the big surprise from this past election, for example, was Cuban American voters in Florida who suddenly sort of voted had a high turnout and voted Republican. Okay? But just from the perspective of P, that's really like we had no idea that this set of people were going to turn out in such high numbers, right? I think maybe Florida Cuban Americans tend to vote. They tend to turn out to vote often. But anyway, okay. Sorry, maybe the surprise was just how they voted. But I think the fact that we don't have that many data points is kind of one of the limitations with trying to apply this to the polling setting. I guess the other issue is also from a polling standpoint, the probability of people participating is so low. I mean, like we were talking about, a given person in the US probably doesn't have a phone. And, the probability of them ending up in one of these polls or responding to a poll is, it's less than 1 or 2%. And I think that's really the issue. That there are lots of people where basically the probability of them participating is 0. And for that huge demographic, there's nothing you can do.
Yeah, thank you, Greg. And maybe we can have one more question. Actually, I have a quick question on your importance sampling example. Yeah, could you? Yeah, do you have a sense of what is the final estimator given by the STP algorithm look like?
Good. Yeah. So what does it do? It right. Okay. So you can think about it as it tries to fix the issue with subgroup estimation and the issue with reweighting. So think of it as, suppose you start with subgroup estimation. So you're going to compute the estimate of the mean on the left half based on the people on the left half. You'll compute the estimate of the mean on the right half based on the people on the right half, and then just output the average of those two. Okay. So what is it going to do? It's going to, instead of outputting the empirical means of these, it's going to regularize each of these means separately according to how big the sample was. Like if you only get one person from the left half, then you should do basically what we did on the very first slide of outputting 1/4 or 3/4 instead of something else if you only have one sample, right? So we're going to regularize our estimate of each half separately. But then also, if we get lots of samples from the right half and very few from the left half, our kind of variance of the left half is going to be bigger too. So we're going to also slightly regularize the mixing weights. So that's kind of what the SDP thing does. It so again, like the answer, the estimate will depend on the empirical averages of these two halves, as well as the number of people in each half that ended up being in our sample. And it's going to kind of do the right sort of regularizations in that, yeah.
I see. So can you see? Yeah. So do you have a sense of, let's say, let's say the expression? Because I think the weight only depends on basically the number of samples in each group. So could we have a sense of the, let's say, how the expression looks like from, let's say, from the practical SDB algorithm?
Yeah. So okay. Yeah. So it's not a in contrast to the regularization, it was just estimating a single coin, this like 1 over square root k plus 1 thing. In contrast to that, it is actually some sort of complicated combination of the number of samples in one group and the number in another. So it's not something super simple. Yeah. So it's not like a linear function of the two sample means or anything.
I see. Yeah. Thank you. Okay. Perhaps we can thank Greg again for the great talk. Yeah. And let's also thank the organizers of this workshop, including the Lauren, Pauline, and Jiaming, and all the speakers for the great talk. And have a nice weekend. Thank you, Greg.
Thank you. Yeah, I'll stay on if anyone wants to say hi.